Oh yes, well, so as mentioned, my one of my videos, Exercise9D, corrupted in terms of its files. So you would find that Exercise9D, we can't access it through YouTube. So I'm making another video again, just kind of briefly describing how to draw derivative functions. So I'm going to have a look at a couple of questions and try to sort of touch base on the things that you need to sort of pay attention to and have a look at, right? So let's try. I'm just going to copy for, let's see, the 6 graphs. Okay. I'm just going to start over here. All right. So your goal is to sketch the derivative graph. And the derivative graph, the only difference or the things that you have to pay attention to are any turning points. So meaning gradient when it's 0, you're looking for when gradient is positive and when gradient of the tangent line is negative. Okay, now traditionally they'll write f dash of x is greater than 0, meaning that's positive gradient. F dash of x is equal to 0. That means you have a horizontal line. So this is a positive tangent gradient, 0 tangent gradient, and then you might have f dash of x less than 0, which means a negative tangent gradient, right? So if I look at each graph, if I were to draw, and each graph, remember, they all have infinitely many amount of points or coordinates. So I'll copy this one over here. So these have infinitely many amount of coordinates. This has infinitely many amount of coordinates, right? Your goal is to analyze, well, what's the relationship between your x values, which I'll do down here, your x values and your gradient. Okay, so what I'm saying is if you had, let's say, this x value here, x equals 1, for example, then at x equals 1, you want to draw a tangent line, which so happens, which I'll draw in blue so you can see, so happens that the gradient is the gradient of the tangent line is actually just the line itself. That's why at this point you can actually find the gradient, because the gradient of this whole entire straight line, doesn't matter which point you choose, the tangent line is the line itself. True? Okay, so then what I'm trying to say is at any point, doesn't matter where, this point, the gradient is the steepness. True? So you got a rise of 1, a rise of 2, and a run of 1, because it says -1 here for the x values, and the y value is 2. So I know this gradient, rise over run, m is currently equal to 2. At any point, it doesn't matter where it is, every point, it's a straight line equation, so the gradient's the same. Yeah, if I were to write the equation of the straight line, it's 2x plus 2 likely. Okay, because it's got a y-intercept of 2. So what we can see is that the gradient at every single point is going to be 2. Doesn't matter what x is, whether x is positive or whether x is a negative value, that tangent line has a gradient of 2. So what does that mean? It just means that when you sketch the graph, okay, so I'm going to do it over here. When you sketch the graph for A, you know that the gradient, no matter what the x values are, so when it's 1, the gradient's still 2. When x is 2, gradient still 2. When x is 3, gradient is still 2. So what I'm trying to say, in relative to this graph over here, if x equals 1, the gradient at this point is still 2. When I look at x equals 2, okay, the gradient at this point is still 2. That's what I'm trying to say. And what we can see is it gives us this nice graph. And that's called our derivative graph, because we're just sketching dy dx by x. Yeah. I think as a starter, it might get a bit confusing with the linear equations, but let's try a parabolic shape. Okay, let's try D. So we've got D. So your aim, remember, is to look at these 3 things, the type of gradients you have. So let's have a look at this. If you look at every single coordinate on this graph, so I'll just draw out random coordinates here. I'm just picking out a few, right? Obviously they gave us -1, 4. We know that if we were to draw a tangent line at every one of these points, at this point, at that point, at that point, the only one thing I know about this graph so far is the gradient is positive. That's a positive gradient. Whereas on this side, the gradient of the tangent line is currently negative. Okay? And one of the things is, well, it went from positive and then 2 went to negative. At some point from positive to negative, it had to be 0. And we all know that the tangent right at the maximum, the gradient is 0. Okay, so there's a few pieces of information so far right now, so I'm just going to draw a quick timeline of what we know. We know so far that there is a gradient of 0 at x equals -1. So you can see at x equals -1, this turning point here, you've got a gradient, which is this point. Gradient of a tangent line is 0. So that means if I'm sketching the gradient by x-axis, so dy dx by x, the derivative graph, then when x is -1, well, what's my gradient? Gradient is 0. So it happens to sit right there. That's when gradient is 0. Whereas all of these values when gradient's positive. This is when gradient's negative. They're all negative. This is all positive. True? Okay, so because of that, well, now that I'm thinking about it, let's look at this graph. If this is -1, any values less than -1 for x, any x values you choose, let's say x equals -2, what you can see is clearly the gradient at this coordinate has to be positive. So already, if I'm looking at this graph over here, the derivative graph, when x, doesn't matter which values I choose, even if I chose -2, when x is -2, the gradient has to be positive. So that means it has to be, there's my values there, it has to be in this upper region. See what I mean? Because I'm saying that the gradient is positive. So for all I care, all I know is that maybe my derivative graph could look like this. Okay? Because it's got a positive gradient. All of these points here, remember, they're not y values. These are describing your gradients. But in my case here, I actually do know what the shape should look like, because this looks like a quadratic equation. Let's say -x². But what we do know is that if we found the derivative of an x² will make it a linear. So from quadratic it becomes linear. So I know the shape has to be a linear graph, but not only that, it's a negative linear graph. So I know it has to look like that. See, when x is, what I'm trying to say is, if you just do a comparison, I'm going to rub all this off here. All I'm saying is, if this is -1, you choose any x values less than that, we can tell that the coordinates will give us a positive gradient. This is the positive gradient region. Okay, don't look at the shape of the graph, just look at the gradient axes. It's positive, so I've drawn it all in the positive region. What we also know is it's increasing. Look at the steepness of each line. It's increasing in terms of value, so therefore my gradient's increasing. That's why it's going up. So it's going all the way up, like the gradient's increasing. Whereas on the other side, when I choose x greater than -1, so let's say 0, 1, 2, 3, you can see that the gradient is slowly becoming steeper and steeper, but negative. So that means when I draw it out, this is what it looks like. It's getting gradually more negative. See, these are your negative values here. It's more negative gradient. Okay, and that's the hardest part of the sketching the graphs, is to remember that you're only sketching the derivative. You're not interested in the y values. You're just interested in when x is a certain value, what is the gradient at that point. Okay, if I have a go at f, for example, so let's have a go at f. Now I know this is a cubic equation, so you can see there are 3 x-axis intercepts. So it's a cubic equation. Derivative should look like a quadratic. So I know the derivative graph should look like one of these quadratic graphs. It could be like that. Okay, so let's analyze it now. Let's analyze the main points that you have, and the whole point of exercise 9D is to analyze those points. Whoops, I've just done something. And let's have a look. So if I chose, now if I like to look at the turning points first, so I can see that at x equals -1, at these points gradient has to be 0. All right, those are the stationary points. So at -1 and 2. So what I do is I say, all right, -1 and at 2, remember this is your derivative graph, so it's dy dx axis. This is my x, and I know the gradient is 0. So I got these 2 points already. At least that's what I know that has to exist, right? That's when x is -1 and gradient is equal to 0. That's what I know. So I plotted the point for -1, 0, yeah? And also 2, 0. The next thing I need is any value less than -1, what you can see is the gradients of the tangent lines are all negative. So that means less than -1, it should be down in this region. Okay, because it's a negative gradient, yeah? So I can already see that it's increasing in steepness. Each line, if you think about it, from 0, it started off flat, and then it started to curve up and up and up and up. So it's getting steeper and steeper, so that means it's a very large negative steepness. So I'm going to draw it out this way, because it's increasing in steepness, increasing in negative gradient. Then in between it, so between, if I just analyze the graph a bit further, so between -1 and 2, I can see that the graph is increasing. See, it's increasing, 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 and then decreasing, decreasing, decreasing until it's 0 again. The interesting thing is that means somewhere between, so you can see this gradient here is not as steep as the gradient at this point. But then somewhere over here, the gradient flattens out. It flattens even more and then eventually becomes 0. So that means at somewhere between here, there must be a maximum positive gradient because it's increasing, right? So that's between what, -1 and 2, somewhere between there, maybe +1, it has a maximum gradient. So for me, when I draw the graph, there's a maximum gradient somewhere, and so it's about here. So it increases, and it comes back down. By the time it gets to x equals 2, which is here, gradient is 0. So that's why I touch the 0 axis. This is when gradient is 0 at that point. Okay, but obviously I had to have a maximum gradient before it returns back to 0. After it hits 0, what you notice is every single x coordinate greater than 2, you have a negative gradient. So x greater than 2, you have a negative gradient, so it has to go back into this region here. Okay, this is all the negative gradient values. So that makes sense, and if you kind of roughly draw it, it should be a parabola. It looks like that, okay? Because I know this is a cubic graph, so if I follow that sort of pattern, naturally it becomes quadratic. Cubic derivative cubic becomes quadratic, yeah? That's the gist of what you do in exercise 9D, okay? It gets tricky when you get graphs that you don't know and you have to predict it. So let's say, for example, the one I did in class, I like F. See, F is good. Let's have a look at F again. So F is nice because, and I'll show you why, it's because it's got that asymptote that we have to sort of look at. Same thing here, so I'm going to draw out my axes again. Alright, let's look at the things I know. There's clearly a turning point here, so at x equals 1, I can already tell the tangent of the gradient has to be 0. So at x equals 1, m equals 0. So that means at x equals 1, so remember this is the derivative graph, dy dx. This is x. At 1, I should have gradient of 0, so that's my point. Okay. Now, after this point, so after x equals 1, any x value is greater than, it's increasing in gradient. True? It's positive gradient, it's increasing. So therefore, this is the positive region, and all the gradients are increasing. So I would say something like that. I don't know. That could be right, but all I'm just drawing is an increase in x value. But notice the x values can only, there has a cap at x equals 2. There's an asymptote, a vertical asymptote here. So that means the x-axis will never pass x equals 2. Gradient will infinitely get larger, but the x-coordinates can never reach x equals 2. Okay, so that's why I've got a vertical asymptote here too. Now this is where it gets tricky. The trickiest part is reading this. What you can see is over here, it's a negative gradient. It's a negative gradient. But remember, this negative gradient over here is flatter than the gradient over here. And it's also flatter than the gradients over here. See, that's the steepest. Somewhere here, it starts to flatten out again, flatten out again, flatten out. Eventually you get to 0. So that means somewhere here, there is the maximum negative gradient. Okay, and then it starts to plateau out. So you can see it starts off at 0 and it starts to increase, 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 and then decrease, 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 decrease. Okay, so if I use that, I'll do it again. So increase, 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 very steep, but you can see it starts to flatten out again. Okay, and the thing is, because there's an asymptote at y equals 3, it will just keep reaching towards the horizontal line because there's an asymptote, but it'll never be a horizontal line, so hence the gradient will never equal to 0. So when you draw it, what you can see is the gradient will never equal to 0. It approaches 0, but here's the thing. You also have to show when does it roughly get to its maximum, and from what I'm seeing, it looks like it has a steepness. The steepest point is somewhere there. So then maybe about 0, it reaches its maximum point, okay, and then it starts to decrease again, but it never reaches 0 because the gradient is approaching that. So think about it, if I draw out these gradients here, they're just approaching. They're all negative, they're getting flatter and flatter and flatter and flatter, but they never equal to 0 because there's no horizontal line, because the horizontal line itself is y equals 3 asymptote. That's why. Okay, so it's infinitely getting smaller and smaller and smaller, and that's what I'm showing in my derivative graph. If you have a look here, it's infinitely getting smaller, so it's getting smaller and smaller and smaller and smaller and smaller and smaller, and there we go. Okay, so this is roughly the graph, and you got to draw out the asymptotes y equals 0. Okay, but that's how you would do exercise 9D question 2F. Okay, and just to finish off the video as well, the skill here is to obviously analyze the gradients, but the one I'm a bit more interested, which it links to what we did last lesson about modulus graphs. Okay, so notice here, this modulus graph kind of looks like this. True? Now the question is it differentiable at this point? Because most of the time we say any maximums, there's a gradient of 0. Problem with this one is, and this is what you're meant to understand, is if you were to draw the derivative graph for this, y and x, at whatever this x value is, let's say x equals 2. When x equals 2, there is going to be a y value, because that has a y value. What you don't know is at x equals 2, is there a gradient value? So when x equals 2, is there a gradient value? That's what you don't know. Because the gradient at this point, the tangent line could be like that, or it could be like this, or it could be like this. So I don't know. At the very top there, I don't know what the gradient should be. Now logically, if you look at the graph that they've given us, where is it? I didn't copy it. No. Let's do this one. Okay, if we have a look at the graph here, we can already see it was from here to here, you get your rise and run, and x-wise it moved up by 1, this one decreased by 1. Okay, so it's -1 over 1. I'm just doing your y2 minus y1, yeah? 5 minus 4, 1 minus 2, 1 over -1. Okay, so the gradient so far between these two, it's negative, so it's going negative, and it's -1. Whereas on the other side, you got 1, 0, 4, so 5 take away 4, and 1 take away 0. Gradient on the other side is 1. Okay, so if we were to draw this graph, this derivative graph of this modulus function, I already know when x, this is where x equals 1, right? And we know the gradient at this point, we don't know what it is. Okay, at this point, we don't know what the value should be, but we do know that anything less than 1, it should be a gradient of 1. So less than 1, so if 1 was here, less than 1, it's a gradient of 1. Okay, so from here onwards, gradient of 1. Whereas from x greater than 1, then the x values, the x values like 2 and whatnot, have a -1 gradient. So -1 gradient would be somewhere down here. Oops, and it should be like that. Okay, the question is, what is at x equals 1? So we've got greater than 1, less than 1, but that at x equals 1, what is the gradient? See, the tricky part to this is, if I approach it from the left-hand side, you see, it's the gradient has been 1, 1, 1, 1, 1, 1. So when I approach 1, you naturally would think the gradient should equal to 1. But then, interestingly enough, if you come from the other end, if you go from left, it's -1, -1 gradient, -1, -1, -1, -1, up until this point. And again, at x equals 1, you get the inclination that maybe m is -1. Now, because there are two discrepancies there, and it could be either, we don't know. Is it 1 or -1? So that's why we put an open circle at the end of each of these graphs. Okay, so just pay attention to that. That goes back to differentiability in last lesson as well. Okay, and just for those who are watching this, last lesson, yes, it was differentiable. The example I did, it was just out of the blue for me, but it was definite that it was differentiable. Okay, so following the checkpoints to check if it's differentiable or not is important. But this is exercise 9D. If you still have trouble sort of reading graphs, come and see me. I'll see what I can do to explain it. But at the end of the day, the most important skill that you got to take for chapter 9 are all the derivative graphs. Can you find the derivative of sine, cos, tan, exponential, log, power functions, chain rule, product rule, quotient rule? That's what you want to take out of exercise 9D. Okay, I hope this helps. But yeah, again, send a message in Schoology. You know, I'll have a look at it, and if there are any questions that I don't, as in if I see, then I'll answer it in my spare time. Okay. Have a good weekend. Sorry for the late video. I've been a bit busy this weekend, just enjoying myself. But you know, back on track, and we've got only about 4 weeks left before holidays. We've got to pick up our pace for you guys to study over the holidays. Okay.